Okay, let's focus our discussion now to the use of the equal area criterion, the single machine infinity boss problem. Okay. Mm, as you must remember, I said before, early before that if we have a power system, any power system, topology doesn't matter. What is important is that we have a generator and there is some transmission systems connecting to infinity bus bar. Topology doesn't matter. My students, they are quite good on matrix method apply for to power systems. Okay, and what is important is that any power system, single machine connected to a bus bar system, can be translated into an equivalent model like this. Okay, and my students, they will be able to calculate that reactance interconnecting the generator and the infinity bus bar. Okay, here you can see this is the equation defining the electrical power that is provided by the generator and arriving to the single bus bar. Okay, and to clarify again, this is a lossless power system. I mean, resistance equals zero, and also there is no capacitive susceptance over here. Okay, well, let's start with something simple. Okay, imagine that we have the system working in a steady state. If the working is if the machine is working in a steady state, of consequence, electrical and mechanical powers, they are equal. There is no acceleration at this machine. The rotor is rotating at constant speed, and there is an initial angle over here. You can see the angle. The angle is delta zero. Okay, using the steady state or pre-fall conditions, you can identify the value of delta zero. Okay, and that is the initial state point. Okay, that is the initial equilibrium point. Okay. And now let's do the following. I will start with a very basic but very illustrative disturbance. Okay, we will do right now is a basic disturbance. I say a few slides ago, I say this is not quite typical. My colleagues from the control room, probably they are laughing because I am talking about this. But what I want to do is a sudden increase of mechanical power. I mean, we have the system working in a steady state. The synchronous machine is delivering power to the infinity bus bar, and suddenly we increase the power from mechanical power zero to mechanical power one. Okay. Of course, I know that some of you will be laughing also because that is a step change of mechanical power. I mean, that is impossible. There is no possibility that a hydropower plant or a gas turbine do something like that. Also, if you try to do something like that, probably you will broke the shaft of the generator. Okay, that is impossible. But for my explanation, it's quite useful. Okay, for my explanation about the use of equal area criterion is quite useful. Imagine that we are moving mechanical power from 0 to 1 at one instant, and that is the 0. Okay, well, what I am showing here is one of the most beautiful. I love this plot. I love this plot because allow me to show you the interconnection between what is the concept that I have been explaining. Okay, let me start with this side. Let me start with the left-hand side. What is in the left-hand side? In the left-hand side, I would like that you understand that this is the power angle. Okay, this is the power angle, and this is the power angle curve. That curve, I say to you, is extremely important for transient stability because define the behavior of your system. Okay, what is on here in this section? Well, over there you can see the disturbance. The disturbance is plenty simple. You can see that the mechanical power is going from mechanical 0 to mechanical power 1. Okay, that is what is happening over there. Is happening at T0. What I'm trying to say, if you go back here, you are at the very beginning. You are at this point. Let me use the pen here. You are at this point here, and suddenly somebody increased the mechanical power to here. Okay. What I'm telling you is that this is the initial point. This is the initial point. Let me do it again. Let me do it again. Okay. This is the initial point, and this is the final point. Okay. You can see here they are coming from the right hand side here. Okay. But what I say is that we are here, and this is the final state. But how do we move over here? Okay. I need that you understand the following. We are starting from A, and we want to go to B. But in real life, the machine doesn't behave like moving from A to B like that. I mean, it's no straight away because they are electromechanical processes that when you make this change on the mechanical power, when you make that change on the mechanical power, you are adding energy to the system, and that energy must be dissipated if we want that the system reach a new state. Okay, and what I want to show you is here below. You can see what is really interesting. Okay, here is a plot. Here you can see a plot of the power angle. To be honest, this is the solution of the differential equation of swing equation. Okay, the equal area criterion is not meant to do this. Okay, it's not meant to do this, but I want to teach you how the things are moving here. I need that you understand. I need that you understand how the machine is moving from this point to this point, and you will realize that the machine go here, and then here, and then stop at this point. That is what I'm trying to teach you. Okay, what I'm trying to say is initially we are here at the point A. We are here at the point A. Suddenly somebody increased the power from here to there, the mechanical power, and this is supposed to be the final state. Okay, we are here, and in theory we want to reach this point over there. Okay, however, from moving from point A to B is quite interesting, because in this area, I don't know if you realize, but because we increase the mechanical power in that region, the mechanical power is above the electrical power. That means that the machine is increasing the rotor speed, and because the machine is increasing the rotor speed, the angle is increasing, and that is basically this region over here. Okay, what I'm trying to say is that the machine start to increase the rotor speed, the machine start to accelerate, but suddenly we have a problem, because the machine is accelerating, is storing kinetic energy. And because the machine has so much kinetic energy, when they reach the point B, the rotor is still accelerating until reach the point B, the point C. In this area, I don't know if you realize, but the mechanical power is below the electrical power. In this area, the rotor is, in this case, still accelerating, the angle is still increasing, but the rotor speed is decreasing. What I'm trying to say is between B and C, we are here. Okay? But there is a problem. There is a moment where uh, mm, there is a moment here at C that the rotor reach a maximum angle, and then you have a problem because now the mechanical power in this point, the electrical power is bigger than the electrical, and then the machine start to decelerate. Then the machine start to decelerate, and now the machine is moving in this way. When the machine reach this point, there is so much kinetic energy, and the machine try to go over here and reach this point. What I'm trying to say is, when there is this disturbance inside the power system, when there is this big change on mechanical power, the machine will try to move from A to B. But the movement between A to B is not like that in a electromechanical system. In reality, the system will go B, C, then go a bit here, then here, then here, oscillate around B, and then reach the point B, okay? In this case, we are assuming that the system is stable, the system is able to absorb the energy related to the disturbance, and the new steady state point will be the point B, okay? And that will be the final state of the system, okay? I am assuming that because from the graphic point of view, you can see if we want to take in account, there are two areas, clear areas over there. One area is represented by the accelerating area. Between A and B, the machine is accelerating because the mechanical power is larger than the electrical power. But then between B and C, that is the area A2, the mechanical power is lower than the electrical power. And in that case, the acceleration is negative. The machine try to decrease the rotational speed, okay? Then the machine will move between around B, between C and A, it will oscillate and try to reach the new steady state point, and that is the point B. What I need that you understand clearly here is that we have an accelerating area because mechanical power larger than electrical, and we have a decelerating area because mechanical less than electrical, okay? Well, now what we want to do is use the equal area criteria. The equal area criteria, I believe all of you can see that we can define here two two areas, okay? A1 and A2. Okay, they are clearly two areas over there, okay? They are clearly two areas. One area that is the accelerating area, A1. One area that is clearly the accelerated one, and one area that is clearly the accelerating area, okay? And what I want that you understand is the following. Okay? This is the maximum oscillation, this is the final state, and this is the original state, okay? There are 3 points over there. But what I need that you clearly understand is that the area number one is basically defined between delta 0 and delta C. And that is the reason that this area is coming from here is mechanical power minus electrical power. That is what you need to see over there, okay? It's important that my students understand how to write this expression, okay? What you need to understand is this is the starting point here, yeah? And the final point, they are defining the limits of the integral, okay? And the other thing that you need to understand is that inside inside the integral part, okay? Then what we need to do is the following, okay? Inside we have, this is the top that is defined in this area, and then this is the lower area, okay? What I'm trying to say is that the area A1 is basically, using calculus, is mechanical power 1 minus the one that is describing below, that is the electrical power, okay? Of course, you can use this expression, and then for the second integral, you will see that is between this and this, delta C and delta max. And here, there are two options. You use this one in order that the area 2 will be positive. The area 2 will be positive if you are taking in account that this is P electrical, and this area here, this is the mechanical, okay? What I'm trying to say, if you use electrical minus mechanical, the area A2 will be positive as we expected, okay? However, if you don't feel comfortable doing that, you can use on the other way, but you must understand that the area 2 will be negative, and then the equal area criteria require those absolute values over here, okay? Okay, this is just a clarification for any one of you that love mathematics, okay? If you love mathematics, you can define this like the curve that is defining the top minus the bottom, and this one, the finding the top minus the bottom, okay? That if you want that this number will be positive, because the areas, they are positive, okay? But if you want to keep using just mechanical minus electrical, there is no problem. You can keep using that, but you need to take in account that what you want to keep equal is the area, the accelerating area must be equal to the decelerating area. Okay. Okay, here I just want to show you, okay, on the right hand side, you have the time domain solution. On the left hand side, you have the equal area criterion, okay? Using equal area criteria, you will see if you can find this value, if this value can be reached, because this value allow that this area, the accelerating area equal to the accelerating area, we are fine, okay? The equal area criteria, what is looking is to identify if the points are possible to define areas that they are equal. If the accelerating area is equal to the decelerating area, we are in a steady state condition. We will reach a steady state condition that is stable, okay? You don't need to do what I plot here on the right hand side. On the right hand side, I plot the response of the system. In this case, this is the power angle, and here the rotor speed, okay? But I plot this because I would like to show my students the practical stuff, okay? The practical stuff, if you are using a power system software, you will get these oscillations, and you will see there is an initial steady state, there is a final steady state, and there is a maximum oscillation, okay? We care so much about this kind of plots because we want to see this important down characteristic over here, okay? If we see that, we will say the system is stable. Now, talking about the rotor speed, you can see here also the rotor speed is decreasing in amplitude and also reaching a steady state. That means this system over here is stable, okay? But the important part here is You must recognize that when the system reaches the maximum angle here is because the machine is reaching the zero rotational speed, okay? This is like the ping pong ball, okay? When the ping pong ball reach the maximum altitude, at that moment the speed is zero and then start to increase again on the other direction. That is what you need to think about when you are considering those plots over there, okay? Well, what is the conclusion here? The conclusion here is quite interesting. Equal area criteria can be used uh, to identify transient stability, okay? What you need to do is identify if the area accelerating area can be equal to the accelerating area, okay? If there is any operating point, any valid operating point that allow those areas accelerating and the accelerating areas to be equal, we will reach a final state, and that state will be a valid steady state that allow the operation and the system will be stable.